Hey, good morning, everybody. I'm here to work what I find to be a very fascinating problem. We have this huge exponential 2,619 raised to the 802nd power. And of course, that's a huge unpronounceable number, and we want to answer the question with minimal computations. What are the last three digits? Now, over here, parenthetically, you can see my estimate, of the size of this number is something somewhat less than 3,200 digits, because what you have is you have 2619, which is a four-digit number, and then so you have 800 four-digit numbers next to each other, and so it can't be any more than 3,200 digits. It's probably closer, I don't know, 2,800 digits. But the fact that we can use what we call modular arithmetic to find the last three digits is fascinating to me, and I want to see if you guys share that enthusiasm. Now, let's get started here. We can use congruence arithmetic, sometimes called modular arithmetic. Congruence has a lot of the same properties as equality. This congruence symbol you see right here, you can almost think of it as an equal sign. Almost everything that's true for equals is the equals relation is true for the congruence relation. This is in the realm of what they call modular arithmetic. Okay, so observe right here that if you the remainder of this number 3129, when you divide by 1,000, is actually the last three digits, 129. You see, because 3129 is equal to 3 times 1,000 plus 129, right? So that's 129 is your remainder. So if we can use the properties of modular arithmetic to actually make some headway on this problem. Now let's get started. So I want to see what you guys think. Now this very first step right here, this is the number we're trying to find the last three digits of. Now it turns out you can scale it down to 619 because of this fact right here. 2619 is congruent to 619 mod 1000. Okay, but it's also true that if you elevate it to the 802nd power, it's still going to have that same property. Okay, and it's basically true because of an algebraic reason. A minus b is also a factor of a to the n minus b to the n. So again, the truth of this statement right here, the truth of this statement right here implies the truth of this statement right here. Now, and just a side note, a special case of why this is true is just the familiar difference of two cubes formula. Notice how a minus b is a factor of a cubed minus b cubed, but it turns out it holds for the general exponent n, all right? Now, I won't say too much about this. I'm very interested in this, but this is called the Euler Phi function right here. And the Euler Phi function counts the number of natural numbers less than 1,000 that are relatively prime. That is, they have no common factor. All right, now, again, I may spend some time doing a video on this, but for now, we're just going to take it as a fact. All right, so it turns out something else that you can prove. Rather than exhaustively write down all the numbers less than 1,000 and check to see if those numbers are relatively prime or have no common factor, there's this really cool result right here that just depends on the prime factorization. It turns out that 2 and 5 are the only prime factors of 1,000, if you think about it, folks. 2 and 5, 10,000 is just 10 cubed, right? But 10 is 2 times 5, right? And so 2 and 5 are the only two prime factors of 1,000. And this formula right here gives you the number. This number right here is crucial. It doesn't seem, I don't really get it really why it works, but I just know that it does. 400, there are 400 numbers less than 1,000 that don't have anything in common with 1,000. That is a number like 1, 3, 5, 7, 21. There's a whole list of numbers, and it would be a pain to try to list them all. It turns out this handy little formula tells us that number is equal to 400. Okay. Now, the big result that really makes this whole thing fly is the fact that this fact right here. In congruence arithmetic, if you take a number a that is relatively prime to 1,000 and to elevate it to what they call this Euler Phi function, which is 400 in our case, you get that big number is congruent to 1. So in many regards, that's inequality. That's like saying something's just equal to 1. If you can learn to think of congruences as equalities, it'll make it a lot easier. Okay, now let's get down to business and see how this works. So let's take a look at this line right here. Okay, we've already shown all of this. Now, notice how I'm using congruent symbols and equality symbols here together. You got to be a little careful with that. They don't mean quite the same thing, but they're very similar in properties. Okay, now what really makes it work, the labor saving, in fact, this is probably the biggest part of the entire proof. If you take a look at this truth right here, 400 is the Euler Phi function, and if you compare this, let's see, I'm trying to get the highlighting going, but right here, this statement right here that I've highlighted, folks, I hope this is working out for you, okay, that I've highlighted right here, is why this statement down here is true. I can't make them both stay highlighted, I guess, okay? But this humongous number, 619 to the 400 power, leaves the remainder of 1 when you divide it by 1,000, all by this result, this Euler's result. Now, the rest of it is fairly straightforward. See how this factorization occurred? Going from, let me highlight the big step right now. There we go. This is getting a little more intelligible for y'all, I hope. See here how this piece right here is just equal to 1 mod n. You can use the word 1 mod 1,000, excuse me. So you see how this piece went away and all you're left with is 619 squared. So that original huge number 2619 to the 802 is congruent to just this piece right here. Now that's quite an accomplishment, right? Now you could have done all this without a calculator. I'll tell you that this number right here, I use the calculator. I will confess I use the calculator here. But you could have done 619 squared by hand. You could have done 619 squared by hand. And notice that you get a number with a remainder of 161 upon division by 1,000, which is what modular arithmetic is. It's just about remainders when you divide the modulus into the argument, into the number, right? So that does it, folks. That's the proof. That's the proof. I hope I didn't do too much talking. You can sense my enthusiasm here. To me, it's just astonishing. Michael Penn on his famous channel does things like 123 raised to the 456 raised to the 789, or these huge expressions like 1 factorial plus 2 factorial plus 3 factorial, all raised to the 100 factorial. I mean, he does some astonishing stuff. I'm still just trying to learn this, but to me, it's amazing that we know that the last 4 digit of this. If you tried to write this down, it would fill up a loose leaf notebook. It's like, well, that's an exaggeration, but we're talking 2,800 digits probably here. What we know now, without any reservation, is that 161 is the last digit of that huge exponential. Thank you for listening.